Greetings. So, today we will discuss the Levinsons theorem, and we got very close to that in the previous class in talking about the scattering phase shifts. And what the Levinsons theorem does is to relate the scattering phase shifts at low energy in the limit energy going to 0 to the number of bound states that an attractive potential can hold. So, let me quickly recapitulate some important results. We considered the resonant part of the S wave scattering in the previous class. Okay, so, there is a non-resonant part and there is a resonant part. So, in the resonant part we considered higher order terms k to the power 4, and we found that the tangent of the phase shift blows up as inverse k. As k tends to 0, the tan delta blows up, right. And if you look at the scattering length, the scattering length goes as 1 over k square, because it is tan delta over k, tan delta itself goes as 1 over k. So, the scattering length goes as 1 over k square, and because the scattering wave wavelength grows as 1 over k square, the tan delta blows up, and when the tan delta blows up to infinity, the delta itself, the phase shift, is like pi by 2, multiples of pi by 2 modulo pi, of course, right. So, this is the typical tangent curve, and let us have a look at this. So, you notice that the tangent of an angle blows up at pi by 2, 3 pi by 2 and so on in half integer multiples of pi by 2, that is when the tangent of the angle blows up. And the low energy non-resonant part, we have already seen the phase shift goes as k to the 12 plus 1. So, it will tend to 0. So, the phase shift tends to 0 modulo pi in the non-resonant region, but then in the resonant part something happens, that the tangent of the phase shift blows up, it does not go to 0, instead it blows up, and what it does is happens when the phase shift is pi by 2 or plus or minus pi. Now, this is a very peculiar effect, and it is happening because of a resonance effect, and we will discuss why this resonance takes place. And notice that the tangent curve reverses its sign at pi by 2, and this is the expression for the scattering amplitude and the partial wave amplitude, which we have seen before. Now, let us evaluate the partial wave amplitude when delta is pi by 2. Now, this is where the resonance takes place, right. So, as delta 0 approaches pi by 2, then the partial wave amplitude, which is this S matrix element S minus 1 over 2 I k, gives the partial wave amplitude. So, this is now cos 2 delta, and at delta equal to pi by 2, 2 delta is pi, and you see quickly that the partial wave amplitude itself goes to I over k. Now, as partial wave amplitude goes as I over k, you can also get what the scattering amplitude will do. It will also go as I over k for L equal to 0, okay, because that is the only thing which is contributing to the scattering amplitude in low energy scattering. Only the L equal to 0 is important, and this goes as I over k, and the scattering cross section itself will go as 1 over k square, because it is the integral over all angles, and the scattering amplitude is independent of angle. So, all you have to do is to integrate all the angles, that gives you the factor 4 pi. So, the cross section blows up as 1 over k square, and this is the 0 energy resonance, which happens at delta equal to pi by 2, 3 pi by 2, 5 pi by 2 and so on. So, the question is, why does this happen? And this is connected to a theorem which was set up by Levinson in 1949, and what it does was to take the 0 of the phase shift at high energy, in the high energy limit as k tending to infinity. So, that is only the reference. So, phase shifts are measured with reference to this as the 0 of the phase shift. So, with this as the reference level, let us first state it for S wave scattering, which is for L equal to 0, and the Levinson's theorem applies for L equal to 0 and also for other values of L. So, let me first state it for L equal to 0. The theorem is the following, that for L equal to 0, as k tends to 0, the S wave phase shift goes to n pi or n 0 pi, 0 the subscript 0 corresponds to the angular momentum quantum number, which is L equal to 0. So, basically delta 0 goes as n 0 pi in the low energy limit, or else it goes to n 0 plus half times pi if there is a resonant bound state solution. Okay. In the event there is a resonance, there is a resonant bound state solution, then the phase shift does not go to n 0 pi. Okay. Now, this is the Levinson's theorem. Now, to indicate the fact that the reference of the phase shift delta is 0 at k tending to infinity, this theorem is sometimes stated like this, that the difference in these phase shifts, the phase shift of the Lth partial wave at 0 energy with reference to what it is at k tending to infinity, is equal to either n pi or n plus half pi. N plus half pi is relevant only in the case of S waves and only when there is a resonance. So, this is the statement of the Levinson's theorem, and to illustrate this I will consider a square well attractive potential. Okay. So, this is just to illustrate the Levinson's theorem, although it is applicable for any kind of attractive potential, but it is easiest to demonstrate it for the square well attractive potential. It is a very simple potential, as you can see, and the potential has got a depth of minus beta square up to a range r equal to a, beyond that it is 0. So, that is the nature of the potential we are going to work with. If you now set up the Schrodinger equation for this potential and you write the Schrodinger equation and rewrite a differential equation for the function y, which is r times the capital R, which is the radial solution to the Schrodinger equation, then specialize it for the S waves, which is for L equal to 0, and then write it in terms of the reduced potential, which is u, which is only scaled real potential V by a factor of 2m over h cross square. Then it simply looks, the differential equation looks in a neater form. So, that is the only reason to carry out this transformation. So, you get a differential equation for the function y, okay, and for this function we have put L equal to 0 now. You consider first discrete bound state solutions. So, the energy is intrinsically negative for discrete bound states, okay, and this explicit intrinsically negative energy is what has been written as minus gamma square. So, that its explicit negative nature is now manifest. Okay. So, this is your differential equation for y, which is little r the distance times capital R, which is the solution to the original Schrodinger equation. So, now you know this, what the solutions are. Now, this differential equation for r less than a is minus beta square. So, you can solve this very easily. Okay. This will be a sinusoidal function, right, for u, which is a constant over this entire range from 0 to a, and outside it is an exponentially damped function. Okay. So, outside the well it will be an exponentially damped state because it is a bound state. So, it can certainly penetrate through the potential a little bit, but then the amplitude will damp out. So, it will damp out as e to the minus gamma r. So, these are the solutions of these two differential equations for the range r less than a and r greater than a, but at r equal to a the wave function and also its derivative must be continuous. So, you just impose the boundary conditions of the continuity of the wave function as well as its derivative, and you can get the derivative of the sine function as well as the e to the minus gamma r function very easily, and from these continuity equations you get a relation which is tangent of this angle equal to minus of root beta square minus gamma square over gamma. So, that is an automatic consequence of the continuity at r equal to a. So, you need to study the properties of the tangent function. Okay, let us say have a look at how the tangent function behaves, and from this behavior we will learn a lot. So, the bound states are given by this solution, which is tangent of this angle, and this angle is determined by properties of beta. Beta is determined by the depth of the potential, right, that is what determines the depth of the potential. And what is gamma? Gamma is the energy parameter. Okay, gamma or eta are the energy parameters, a is the range of the potential. So, your equation, which is tan theta equal to minus this angle over gamma, can be written as this ratio can be written as xi over eta, and if you look at the relationship between xi and eta, then the relationship is given by xi square plus eta square becomes equal to constant, which is determined completely by the properties of the potential. A is the range of the potential and u0 is the depth. Okay. So, u0 a square is what determines the strength of the potential, how deep is it, that is u0, and how far does it have an influence, that is the range of the potential. So, u0 a square is the strength of the potential, and xi square plus eta square equal to u0 a square is what must also be satisfied, and the other relation that must be satisfied is that tan xi and minus xi over eta, these are equal, right. So, the bound state discrete energy levels are then given by the intersection of these curves. So, this is the relationship between eta and xi, which describes a certain family of curves. Here is another relation between xi and eta, which is another family of curves, right, and the intersection of these two will give you the solutions to the discrete bound state energies. Now, what happens is, because of this peculiar nature of the relationship between xi and eta, the solutions being given for the r less than a region and r greater than a region by these two solutions. Inside the well it is sinusoidal, outside the well it is exponentially damped. So, that is the nature of the square well potential, and in this range between pi by 2 and 3 pi by 2 you get one bound state. In the region between 3 pi by 2 and 5 pi by 2 you get two bound states. Between 5 pi by 2 and 7 pi by 2 you get three bound states, and as a beta increases the number of bound states increases, but not continuously, only where it crosses pi by 2, then 3 pi by 2, then 5 pi by 2. So, it must go through this pi by 2 or 3 pi by 2 or 5 pi by 2 to pick up the next bound state. Now, that has to happen, and the number of bound states increases as you go from left to right in this figure, and to understand it I will take you back to what you probably studied in your first course in quantum mechanics, and we will just do very quickly a one dimensional square well. Okay, just to recapitulate the method, and you will see that it is exactly the same algebra which is used over here. So, we will very quickly do a one dimensional square well. So, you have got a square well potential in one dimension along the x axis. The potential is V0 in the region minus A to plus A, okay. The potential is 0 in this region, I am sorry, and it is V0 in the region less than minus A on the left of this, and it is equal to a constant V0 for x greater than A. So, that is the nature of the one dimensional square well that we will consider. So, there are 3 regions. The potential is V0 in region 1 and 3, it is 0 in the region 2, that is the square well. You set up the Schrodinger equation for this one dimensional problem. You have solutions to the Schrodinger equation in the 3 regions. In region 1 and 3 the potential is V0, in the region 2 the potential is 0. So, you solve these differential equations, okay, and you solve this differential equation for E greater than 0, and you can solve for E less than 0, okay, depending on what kind of solution you are looking for bound state solutions or for continuum solutions. And then if you look at this expression, you find that in region 1 the coefficient f must be 0, because in region 1 x is negative and this term will blow up, whereas in region 3 the g e to the beta x will blow up. So, g coefficient must be 0. So, the solution in region 1 is only d e to the beta x. So, mathematics gives you 2 solutions, but physical boundary conditions tell you that one of these coefficients must be 0, and this is the nature of the solution when you have bound states, when the V0 which is 0 in the well, when this is greater than E, okay, because in the well the potential is 0, and for bound states E is less than V0 which is less than 0, okay. So, the bound state solutions will be intrinsically of negative energy. So, these are the solutions now, and these are the 3 regions: solution in region 1, solution in region 2 and solution in region 3. Now, what do you do? The solution must be continuous at both the boundaries at x equal to minus a and x equal to plus a. So, the wave function must be continuous and the derivative of the wave function should also be continuous. So, this is the continuity of the wave function at x equal to a, and this is the continuity of the wave function at x equal to minus a, and there are 2 relations, one coming from the continuity of the wave function and the other coming from continuity of the derivative of the wave function, because this is a second order differential equation. So, the first order of derivative should also be continuous. So, the Schrodinger wave function is of course an analytical function, and these are the 2 relations from which you can get the relationships between the different coefficients, and you can solve these equations by combining. If you subtract this equation from the one at the top, you get twice a sin alpha a, because this term will cancel this, you get c minus d e to the minus beta a. So, these are the usual things that you do in your first course in quantum mechanics, and you can easily get these relations which must be simultaneously satisfied, right. And when you satisfy these equations, you get certain solutions. You get one class of solutions if a is equal to 0 and c is equal to d. If a is equal to 0, then the right hand side should also be 0, that makes c equal to d, and if c is equal to d, then this is what happens, that c plus d becomes twice c, and 2b cos alpha a becomes twice c e to the minus beta a, okay. Likewise, 2 alpha beta sin alpha a becomes, this is c plus d becomes twice c. So, it is twice c beta times e to the minus beta a. So, this is one class of solutions that you get. What essentially it means is that if 2 alpha beta sin alpha a is equal to 2 c beta e to the minus beta a, this solution is completely, you can strike off the factor 2, and essentially you get alpha tan alpha a equal to beta. That is the relationship that you get. Now, this relationship must be satisfied to get a bound state solution, and from the other condition, if b is equal to 0 and c is equal to minus d, if b is 0, then the right hand side c plus d will be 0. So, d will be minus c, and in this condition you get alpha cot alpha a equal to minus beta. So, there are two possibilities which emerge. Okay, one is alpha tan alpha a equal to beta, and the other is alpha cot alpha a equal to minus beta. These are the two possibilities. Can they be simultaneously satisfied? If both are satisfied, then see what you get from a multiplication of these two relations. You get tan square alpha a equal to minus 1, which will make alpha imaginary. So, that will not work. So, you get solutions either from this or from the other, but you do get solutions from one or the other. Okay. So, these are the two possible sources of solutions, and one possibility is this alpha tan alpha a equal to beta, and this happens when a is 0 and c is equal to d. So, this is one condition, and in this condition if you put xi equal to alpha a and eta equal to beta a, then this relation alpha tan alpha a becomes xi tan xi equal to eta, right. Now, you will be interested in examining the solutions when xi is positive. Okay. So, the other relation xi and eta must satisfy is if you look xi square plus eta square, then you get a square 2 m v 0 over h cross square, which means that 2 m over h cross square being constant, xi square plus eta square equal to constant determined by v 0 a square, and v 0 a square, which is what determines the strength of the potential. Okay. So, xi square plus eta square equal to a constant, it has to be a constant for a given potential, okay, because the potential is completely determined by just two parameters. One is the depth of the potential, which is v 0, and the second its range, which is a. These are the two parameters, and these two parameters completely define the potential, and they define actually the capability of the potential to hold a bound state, which is why it is called as the strength parameter. And this, as you can see, is an equation to a circle between xi and eta. If xi square plus eta square is equal to constant, then it is an equation to a circle. So, the solutions are given by the intersections of the relation xi eta xi equal to eta and circles defined by xi square plus eta square equal to this constant. And there are a number of circles which are drawn over here. You can see there is one circle, second circle, third circle, and these circles are of three different radii: xi equal to 1, xi equal to 2, xi equal to 3.5, right, or this is actually 3.46. It is a square root of 12 which has been used in this figure. This is a figure which I have taken from Schiff's quantum mechanics. So, this is the reference for this figure. This is straight out of Schiff's book, and you will get solutions whenever these circles intersect the relationship when eta is equal to xi tan xi. Now, this is how the tan theta figure looks like, and if you multiply tan theta by theta, you get xi tan xi, right. So, tangent of the angle multiplied by the angle itself is what gives you xi tan xi, and this has been plotted on the y axis. So, this is not exactly the tangent curve, this is tan xi multiplied by xi, and this curve intersects these circles, and wherever it intersects is where you will have a bound state. So, now notice that the radius of the circle is determined by the strength of the potential, because this is drawn for v 0 a square equal to h cross square over 2 m, that is when xi will be equal to 1, right. This is drawn for xi equal to 2, which is when v 0 a square will be equal to 4 times this, right. So, that is how you are getting the different radii, and they correspond to a different strength of the potential, and the intersections of these circles with the eta equal to xi tan xi gives you the solutions. So, here are the solutions, you get the first solution over here, the second intersection is what you get over here, then you get 2 bound states for this circle. Okay. You get 2 bound states for this circle, whereas for these 2 circles you get only 1 bound state, because the potential must cross a certain minimum strength. A potential of an arbitrarily less strength will not be able to hold a bound state, only if it becomes sufficiently deep or sufficiently wide ranged. A is the parameter V0 A square, actually it depends linearly on the depth and quadratically on the width. Okay. So, the potential becomes stronger quadratically by the width and linearly by the strength. So, for a square well, of course, but other potentials have got more complicated forms, but this is how you get different number of bound states depending on what its strength is. And there is a separate family of solutions which I mentioned. When you get b equal to 0 and c equal to minus d, you get the second family of solutions, and in this case also you get one solution for these 2 values of the strengths. Okay. So, each circle represents a particular strength of the potential, and depending on what is the radius or what is the value of the strength of the potential, you get those many bound states. So, notice that if V0 A square is equal to h cross square over 2m, for the first circle which has been drawn for xi equal to 1, there is no bound state at all. Okay. So, the potential has got a depth, it has got a range, but it does not mean that it can hold a bound state, it cannot. So, unless the potential is sufficiently deep so that this parameter crosses pi by 2, okay, it cannot hold a bound state. So, now we go back to our problem of the square well potential. Yes.
So, in the previous slide,
yeah,
the h square V naught h square is equal to h square by 2m.
Yeah.
That can hold a bound state in the other set of solutions, right? I mean the A is here.
Yes.
But
Yes.
how we define that? How we know that which is the actual set of solutions?
Well, that you will know it from the parity of the solution. The actual solution itself will come from different boundary conditions, and from that you will get the nature of the solution, because in one case you have got one set of the constants which goes to 0, in the other case it is the other set of constants which goes to 0. So, you can get solution from one or the other, but never simultaneously from both, because sure, but there are 2 linearly independent solutions. So, you get solutions from one or the other, not from both. You can get solutions from both if the boundary conditions are satisfied for both. So, for the spherical square well, now we are not talking anymore about the one dimensional square well, but let us go back to the spherical square well. We have already seen that the continuity of the solutions at r equal to a requires us to have the solutions satisfy this relationship between xi and eta, where xi and eta are determined by the potential strength parameter which is related to beta and a, and the energy of the solution under consideration which is coming from gamma. Energy is minus gamma square for bound states. Okay, it is intrinsically negative, so it has been chosen to be minus gamma square. So, here again we find that xi square plus eta square equal to the strength of the potential. This is again an equation to a circle. So, it is a very similar situation as we have seen in the previous case, but for a one dimensional square well we had xi eta xi, whereas in this case it is eta times tan xi equal to minus xi. So, this relationship, the family of curves this time is different. Okay. So, if you remember here, this relation was xi tan xi equal to eta. This was the relation for a one dimensional square well. Okay. Now, it is not xi tan xi equal to eta, it is eta tan xi equal to eta tan xi equal to minus xi, or eta is equal to minus xi over tan xi. Okay. Eta must be equal to minus xi over tan xi. So, that is the relation. So, if you plot eta versus xi, you get a family of curves, and these curves are drawn over here. So, this is one curve which describes the relationship between eta and xi. Then this is the part of the curve in this part of the value of the angle xi. Angles xi are indicated in radians in this, and there are circles also drawn which are given by xi square plus eta square equal to the strength of the potential, and there are circles drawn with different strength parameters for different values of the radius. So, here is a circle drawn for radius xi equal to half, this is for xi equal to 1, this is for xi equal to 2, and so on, right. So, there are a number of different circles, and each circle represents a particular strength of the potential. Now, this is the value of pi by 2, and notice that this is 1.57 on this axis, right. So, this is pi by 2, and below pi by 2 this curve is negative, the tangent, the xi, this curve is negative, the xi over tan xi. Okay. The minus xi over tan xi is negative. Now, because this is negative, you do not have any solution for anything less than this. For any value of xi less than this, you do not have a solution, and you will get the first solution only after the value of xi crosses pi by 2. So, the solutions will come from the intersections of these two curves, and the number of times you have a crossing of a particular strength with this family of curves is the number of bound states that potential will hold. Okay. So, now if you take the circle with radius 2, okay. Now, the circle with radius 2 has got a value which is greater than pi by 2, pi by 2 is 1.57. So, this is more than pi by 2, and for this you will have one crossing, and that is the solution you get, right. What happens if xi is equal to 3? If the radius is equal to 3, you have increased the strength of the potential either through u0 or through a, it does not matter what. Okay. You can increase it anyway, either by making it deeper or wider or both, but if it now becomes given by u0 a square equal to 3, no, or the square of 3, the radius is 3, then again you have got one crossing. What about 4? What do you expect? Again you have a single crossing, right. Now, here notice that you have got only a one bound state. The first bound state you get only after crossing pi by 2. So, for anything less than pi by 2, the number of bound states is 0, there was no crossing for these smaller circles. After the circle became large enough so that it crossed pi by 2, you get one bound state, and you continue to get one bound state till you hit 3 pi by 2. Okay. So, here this is 3, this is 4, but it is still less than 3 pi by 2, and you get only one crossing. So, you get only one bound state. Now, what happens if the radius is 5? now it has crossed 3 pi by 2. Okay? And because it has crossed 3 pi by 2, you will get 2 bound states, because it crosses at 2 points. The same circle crosses the curve xi versus eta versus xi, where the relationship is given by the equation that must be satisfied by the equation of continuity at the boundary, right. The wave function must be continuous, the derivative must be continuous. So, this condition must be satisfied, and you get 2 bound states for xi equal to 5. For xi equal to 6, again you will get 2 bound states. Okay? And it will remain the same number till you get to 5 pi by 2. When you cross 5 pi by 2, then you will get the next bound state, because we have seen that at pi by 2 you get a resonant bound state. Every time you get pi by 2, 3 pi by 2, 5 pi by 2, you get resonant bound states. This is what we have seen earlier. So, in this range from 3 pi by 2 to 5 pi by 2, you get 2 bound states, thanks to Pranav and Sayantan who did the calculations in the graph for me, and these are the graphs which have been used over here. And essentially what we find is what I mentioned earlier also, that for this square well spherical potential, since these conditions, these wave functions are the ones which give you the solutions to the Schrodinger equation, and from the continuity of the wave function and the continuity of its derivative at r equal to a, the number of bound states is 0 till a beta becomes at least pi by 2, and between pi by 2 and 3 pi by 2 you get 1 bound state, between 3 pi by 2 and 5 pi by 2 you get 2 discrete bound states. Then in the third block with range pi, between 5 pi by 2 and 7 pi by 2 you get the third bound state, and so on, right. So, that is how you get, and essentially what we have seen is how the number of bound state changes when the strength of the potential is, it is parametrized through this angle as we have seen, and this angle must go through pi by 2 or 3 pi by 2 or 5 pi by 2 and so on. So, we have considered the bound states. Now consider the scattering states for positive energies. Okay? Now energy is not intrinsically negative, it is intrinsically positive. Okay? These are the solutions for the scattering or the continuum states, and for this the solutions of course are different because the boundary conditions are different, and you set up the Schrodinger equation. Once again we consider L equal to 0, and for continuum states the energy goes as k square, and for this the solutions are different for r less than a and for r greater than a. For r less than a you have got sinusoidal solutions, and for r greater than a you do not have exponentially damped solutions anymore, because these are continuum solutions, these are not bound, so they are oscillatory. Okay? And that is the reason you get sinusoidal solutions, but the sinusoidal solutions will have a phase shift. Okay? That is the phase shift of the partial wave. The partial wave under consideration is L equal to 0, which is the S wave. So, that is denoted by the phase shift delta 0, because with respect to the continuum solutions for free particles, the solutions in the presence, the scattering solutions in the presence of a potential are the same except for a phase shift, and the phase shift is delta. It is L pi by 2 as we know, right, but L is 0, and then in addition to L pi by 2 there is a phase shift which is introduced by the potential, which is the scattering phase shift delta. So, that is the delta 0 that we now have in the solution in the asymptotic region r greater than 0. Now, we impose the boundary conditions at r equal to a. So, these two solutions must be equal and their derivatives must also be equal. So, the derivative will give you the cosine term in both multiplied by the factor which multiplies r. So, in this case it is beta square plus k square, in this case it is k, right. So, these are the two equations which result from the continuity of the wave function and continuity of its derivative. So, these two solutions must be these two equations must be satisfied, and when you divide the first equation by the second, you get the relationship between the two tangents, okay. And then you can manipulate this result by a little bit of very simple algebra by doing cross multiplication and rearranging the terms. So, I will not go through these steps in detail, it is very straightforward. All you are doing is rearranging the terms so that you get the tangent of the phase shift, okay, which is tan delta. So, tan delta is what you are looking for. So, you rearrange the terms and you find that tan delta is given by this relation. You can write it, change the sign as well, and you get the tan delta to be given by this ratio, okay. It is just a rearrangement of the terms. So, this is the final expression for tangent of the phase shift that you get, and you can take this k from right to the left by dividing both sides by k. So, the first term becomes tangent of this angle, and in the second term you have got this beta square plus k square square root divided by k. Now, notice that tan delta by k in the limit k going to 0 gives you the scattering length, okay. So, we have got an expression for the scattering length, and the scattering length being given by this relation in the limit k going to 0, you let k going to go to 0. So, this first term becomes tangent of a root beta, the second term becomes minus of this root beta square plus k square over k in the limit k going to 0 will become beta a, okay, because you have got a tan k a over here which goes to k a in the limit k going to 0, okay. Tan theta goes to theta in the limit theta going to 0. So, k a goes to k a, and that k cancels this k, right. So, you get this numerator, in the denominator you get root beta square over here, and then you get from which you get beta. So, alpha becomes equal to a minus tan alpha beta by beta. So, that is the expression you get for the scattering length, and you can now make a table which I have borrowed from Wu and Omura's very nice book Quantum Theory of Scattering, which I strongly recommend, and this table gives you the number of bound states in the first column. Then here you have got the potential strength parameter. We have defined it as u0 a square. This is the square root of u0 which is beta, and this is the square root of a square which is a. So, this is essentially the strength parameter. This gives you the k cot delta. It tells you how the parameter x changes in this domain as beta a changes from 0 to pi by 2. This tells you how the scattering wavelength changes in this corresponding region of the potential strength as it changes from 0 to pi by 2, and you get the phase shift which goes to 0 when the number of bound states is 0. Then when the phase shift is pi by 2, that is when you get the first resonant bound state. That is when the electron is just about to be bound, because it is resonantly bound, and that is what I have indicated by this asterisk over here. So, this is what is sometimes referred to as the half bound state, because it is resonantly bound. For any depth less than this it will not be bound, for slightly more than this depth it will get bound. Then you have, if the strength parameter increases beyond pi by 2 till it gets to pi, the number of bound state remains 1. In fact, it remains 1 even when the strength exceeds pi till it gets to 3 pi by 2, because till it gets to 3 pi by 2 the next state does not get bound. We have seen that in the solution, that the next bound state is what you get when the depth parameter, the strength parameter changes from pi by 2 to 3 pi by 2. That is when you get the next bound state, and at this the phase shift becomes 3 pi by 2. So, the phase shift goes from 0 or it is pi by 2 or it is pi or 3 pi by 2 or it is 2 pi in this case when the number of bound state is 2, when this parameter exceeds 3 pi by 2 and so on. So, essentially this is a manifestation of the Levinson's theorem, that the phase shift for S waves is an integer multiple of pi in this case, right. So, it is either 0 pi or 1 pi or 2 pi and so on, where the number multiplying pi is the number of bound states, or else it is, if you have a resonant bound state, then it is half integer multiples of pi, like 0 plus half times pi, because this will become pi by 2, the phase shift becomes pi by 2 or 3 pi by 2 and 5 pi by 2 and so on, right. So, that is the basic resonance theorem, that for S waves the phase shift, the 0 energy phase shift is either an integer multiple of pi or it is a half integer multiple of pi when there is a resonance. Okay. So, this is the resonance, this is the Levinson's theorem, and when you have a resonance you have 0 energy resonance, the cross section goes as 1 over k square as we have seen, and this is a very powerful theorem. It is valid not just for L equal to 0, but for any value of L. The phase shift is, the 0 energy phase shift is always equal to n pi. It is only in the case of 0 energy or 0 L equal to 0 partial waves, which is the S wave scattering, that you have these resonant bound states, in which case the phase shift becomes half integer multiples of pi. Okay. So, if there are any questions I will be happy to take. Of course, this theorem we have demonstrated for square well potential, but it is valid for other attractive potentials no matter what the shape of the attractive potential is, and what Sayantan and Pranav are working on are the bound states of a cylindrical potential. Okay. It could be any potential, it does not matter what is the nature of the potential, it does not even have to have a very simple geometry, it may have some very complicated dependence on R. Any physical potential will eventually go to 0, it has no effect, no influence at infinity. So, it will have a certain range, there may be a sharp cut off or it may taper off rather slowly. So, no matter what it is, if you have an attractive potential, then it will have bound states subject to certain conditions which are discussed over here in terms of the strength of the potential parameter. For square wells it is very easy to define this strength because it is just u0 a square. You cannot define it in very simple terms like u0 a square for other shapes of the potential so easily. Nevertheless, the idea of a strength of the potential is valid for any attractive potential, because given an attractive potential it is not guaranteed that a bound state will exist, and some minimal conditions, some threshold conditions will need to be satisfied, and depending on when that condition is satisfied you will have a bound state. And if you make the potential deeper or stronger than that, it does not automatically mean that you will have the next bound state, because another threshold condition will have to be satisfied to pick the next bound state. So, we have found that for the square well potential the next bound state can result only when the strength parameter increases such that our parameter goes to the next half integer multiple of pi by 2. So, from pi by 2 to 3 pi by 2 you have got only one bound state, from 3 pi by 2 to 5 pi by 2 you get the next bound state. Okay. So, that is the Levinson's theorem, and in the next class we will discuss some further aspects of low energy scattering. In particular, I will introduce the effective range formalism developed by Schwinger, Betti, and so on. So, thank you. If there is any question, I will be happy to take.
Previous slide, you are calculating delta by just putting that beta A condition into the tan delta equation.
Yeah. Yep. Yes. As k tends to 0, typically the phase shift goes as k to the 2l plus 1. So, it goes to 0, and it goes to 0 in integral multiples of pi. Okay. So, it goes to 0 in the integral multiples of pi. The cross section goes to 0 as the phase shift goes to 0, right. But the number of times this happens, this value of the integer must change as the potential gets stronger, because the potential has already crossed pi by 2, it has to cross pi by 2 to pick the first bound state. If it does not cross pi by 2, it cannot hold a bound state. Okay. So, this really enables you to provide an absolute value to the phase shift. So, it is not just 0 modulo pi, but what is the coefficient of pi is determined by the number of bound states it holds, because the number of bound states is equal to 0 up to pi by 2, it is 1 between pi by 2 and 3 pi by 2, and only after 3 pi by 2 it becomes twice pi. After 5 pi by 2 it will become 2 pi. That is what makes it n plus half times pi. But then the phase shift in between, as k tends to 0 in the non resonant region, it must go to 0 modulo pi. So, it will go as 0 pi, 1 pi, 2 pi, 3 pi, and so on. Okay. So, typically the phase shift, 0 energy phase shift, is equal to n pi, where n is the number of bound states. It is a very powerful theorem, and it has got many applications in nuclear physics and atomic physics. Thank you.